Hi, welcome back to another video in the CMOS VLSI series. This is going to be the most interesting video in the series, as we will now learn how to create our own custom logic circuits using transistors. The benefit of making our own custom logic to just using a microprocessor to pull the inputs again and again to compute the output is that our logic executes as fast as the transistors can react. Another benefit, since we are using the CMOS family type, is that our logic consumes almost no current, and that is in the region of nano to picoamps. As a matter of fact, the only electricity consumed is only due to the tiny leakage current of the MOSFETs, or when the states are changed as some gates need to be charged or discharged. This definitely beats every microprocessor out there. Now, this video heavily builds upon the last two episodes, which are the transistor and the NOT gate, so it's strongly advised to go through these videos firstly if you haven't already done so. You'll find the links in the description below. The trick we use to making gates is as simple as putting transistors in series or in parallel. Let's examine two circuits. A gold glow on the wires denotes a positive voltage, whereas the aqua glow denotes a negative one. In the top circuit, two transistors are put in series in a circuit containing a power source and a load, such as a lamp or a motor. If both transistors are off, the continuity of the circuit is broken and the load cannot get any power. If we turn on MOSFET A, the circuit continuity is still broken at MOSFET B. If we turn on MOSFET B only, since no current can pass from MOSFET A, the continuity is again broken. However, if we turn both MOSFETs on, the circuit is now complete and the load is powered up. Since we need both MOSFETs A and B to turn on, we have effectively created a logical AND. Now, let's examine how the bottom circuit behaves. The MOSFETs in this situation are configured in a parallel manner. If we turn on MOSFET A, the load is powered up. If we turn on MOSFET B, again the load is powered up. The load is of course powered up when we even turn both transistors on. Since we need MOSFET A or B to power up the load, we effectively have created a logical OR. When we design our logic, we always draw the positive rail on top and the negative rail at the bottom. Recall from the last video that a NOT gate has two parts, the P part and the N part. If we connect the input to high, the output becomes low as the N part gets energized. If we connect the input to low, the output becomes high as the P part gets energized. Now, suppose we want to create a two-input AND gate. In CMOS, when we design a gate, we start by designing in the N part. Since we want an AND, we will put two transistors in series in the N part. Both of them will need to be on for the ground signal to reach the output point. Since we want the P and N parts to turn on in an exclusive manner, when we put transistors in series in the N part, we put transistors in parallel in the P part and vice versa. If you're wondering how this can be, well, this is a direct result of the De Morgan's laws, where they state NOT of A and B is equal to NOT of A or NOT of B. The top MOSFETs or our P part must turn on exactly in a complementary manner to the bottom MOSFETs or the N part. So for the A and B of the N part, we want a NOT of A and B at the P part, or a NOT of A or NOT of B by following the De Morgan's laws. Since the P-type MOSFETs already turn on in an inverted manner to the N-type ones, they are already not A, not B, so we just OR them together by putting them in parallel to fulfill the rule. Now let's evaluate the behavior of this gate. We wanted an AND gate, so for all the inputs, the outputs should be these. Let's see what we get. If A and B inputs are both high, the two top MOSFETs will be off. Remember, they need a negative charge on the gate compared to the source to turn on, and they currently have 0 voltage difference on these pins. However, both of the bottom transistors will be on, so our output will be low. Now, if both A and B are low, both of the N-type transistors will be off, while both P-type transistors will be on, thus pulling our output high. If any of the two inputs A or B is high while the other is low, Since one of the N-type transistors will be off, they cannot form a continuous path of current to our output, so the N part of the circuit is effectively off. On the P part, either the A or B P-type transistors will be on, pulling our output high. So, what do we see? We expected outputs for an AND gate and we got exactly the opposite ones. We got a NAND gate instead of an AND one. This happens because we are designing our logic within a NOT gate. To create a true AND gate, we need to put an inverter at its output. Contrary to what one would expect, the native gate for CMOS is a NAND one and not an AND one. If we wanted to create a 3-input AND gate instead of a 2-input one that we have here, we would just put 3 N MOSFETs in series in the N part and 3 P MOSFETs in parallel in the P part. As a matter of fact, you can extend your AND gate this way to as many inputs as you like. Let's create a 2-input OR gate now. We start again designing our gate in the N part of the circuit. A 2-input OR gate needs 2 N transistors in parallel in the N part, and since we use transistors in parallel in the N part, we put transistors in series in the P part, following the De Morgan's rules as before. If any or both of the inputs are high, the N part will turn on, pulling the output low. If both inputs are low, the N part will be off, while the P part will be activated, pulling our output high. Of course, since we are designing in CMOS, our resulting gate is a NOR one instead of the OR gate we are aiming for. To make it an OR gate, we put again an inverter at its output. To make it a 3-input OR gate, we would just need 3 N MOSFETs in parallel in the N part and 3 P MOSFETs in series in the P part. You can again extend the inputs this way to as many as you like. NAND and NOR are considered universal logic gates, which means we can create any other logic gates using them. To make any complex gate, we can start by its truth table so that we can express it as a combination of NOTs, ANDs, and ORs. Let's have a look at how to create an exclusive OR gate. The truth table for XOR is this. We see only these 2 lines outputting true, so we can express this gate as not A and B or A and not B. For this kind of analysis, I strongly advise you to have a look into Karnaugh maps if you aren't already familiar with them. Now let's try to implement this. We notice that we want a not A, so we must make an inverter for the A signal, outputting an A prime signal. We will not draw the inverters for this example, as we have up to now extensively seen how to implement a NOT gate. We rewrite not A as our new signal A prime. We also want a not B, so again we must make another inverter for our B signal that gets us a B prime signal. Since we both now have A prime and B prime signals, we can write XOR as A prime and B or A and B prime. We start our gate in the N part. A prime and B are 2 MOSFETs in series since it is an AND. A and B prime must be in parallel to A prime and B since it is an OR. Now that we have put A and B prime and A prime and B in parallel in the bottom part, we put them in series in the top part. The gate is almost complete. We now have an XNOR gate, exactly the inverse of the XOR we want. To complete our gate, we put an inverter at its output. We have now pretty much implemented the logical part of our ALU circuitry in the CPU. But what about the arithmetic part? Well, all the arithmetic operations are carried out by clever combinations of the gates we just saw. If you really want to see how an adder is implemented, you can always look up the full adder, or if you want to see how a multiplier is implemented, you can look up the binary multiplier. You will find links in the description section of this video. Now stay tuned for the next episode where we will see how we lay our MOSFETs in a linear fashion on our CPU die and also examine their performance. If you have any questions or comments, please leave them in the comment section below and I will try my best to answer any of your questions. Thanks for watching and see you again in the next episode.